All right, let's next talk here about a couple of applications of the exponential and logarithmic functions. We've already mentioned application of the exponential, and that is what I have on the first line here is the compound interest. And there were two formulas, as you recall. One of them was something if we have compound quarterly, compound monthly, if that's the way our compounding is working, then our formula is A equals P times 1 plus R over N to the NT power. The other formula is a lot nicer. That formula is simply A equals PE to the RT power, PERT. A equals PERT. Remember the difference between when we use these, this one, when do we use this one? This one we use if it's compounding continuously. The one on the right is used when you compound continuously. The one on the left here, the longer one, that's if you're compounding quarterly, compounding monthly, daily, anything but compounding continuously, we're going to use that formula on the left. All right, so let's look at a couple of these. We've already looked at some before, but these have another little twist to them. Let's look at number one. If $5,000 is invested at a rate of 7.15% compounded quarterly, how long will it take for the investment to grow to $7,500? All right, well, again, focused on how often your compounding is, and in this case, compounding is quarterly, and so what does that mean? Which formula, the right one or the left one, do we use in that particular case? If it's compounding quarterly, yeah, we're going to use the one here on the left. We're going to use A equals P times parentheses 1 plus R over N to the NT power. All right, so let's start by using that one. We'll start by figuring out where the different pieces go. We've got $5,000, so where does that go? That's the amount we start with. Yeah, that's our P, the value of P. So we have 5,000 on the right, parentheses 1 plus. R is the rate. Well, of course, the rate is 7.15%, but we do have to move the decimal place 2 places over, so that turns into 1.0715 is what we use for the rate. So that would go right here at the top of this line. Divided by, now N, the N is designating how many times per year the compounding occurs. And so since we're compounding quarterly, quarters being 4 times per year, that would mean N equal 4 here, wouldn't it? Yeah, so 4 we'll go in the place of N, and that goes in a couple of places. It goes down below, and then it goes in the exponent here. Now what about T? Well, we're looking for how long, and so T is our unknown. So we're just going to leave T in the equation for now, which leaves us only one variable there, and that is A. What is A? Well, A is the future amount, and so we want our investment to grow to $7,500, so that's our A. A is 7,500. Okay? All right. So, here, yeah, mentioning this type of equation now because notice this is an exponential equation, and we're going to have to solve for T. And notice where T is. T is in the variable. Let's go ahead and let me go ahead and simplify with the parentheses. So that would be 7,500 equals 5,000 times. So we divide 0.0715. Divide that by 4. And that's going to give us, it's a long decimal, 0.017875. But I don't want to round off. You round off too much before you get to the end, it'll mess you up. So I'm going to leave that and add that to 1, so that'd be 1.017875 to the 4t. So the parentheses there is that. Okay, so like we were saying, this is an exponential equation, and the way we solve exponential equations of this sort is, well, ultimately we want to get it and take the natural log of both sides. So that'll allow us to bring down the power, get the t out of the variable. However, before I do that, I need to get rid of this 5,000. And I can't multiply the 5,000 inside there because of the power. So what I'm going to do with the 5,000 is divide. I'm going to divide both sides by 5,000. Because what that'll do then on the right is 5,000 cancel. Now 7,500, divide that by 5,000. I do believe you get 1.5, yes. So on this left side we have 1.5, and on the right we have 1.017875 to the 4t power. All right. Now what? Well, now what we'll need to do is, like we said, we need to get the t out of the exponent. It's up here in the exponent now. And to do that, I can't do that as is, but if I had a logarithm, I could do that. And so that's what I'm going to do. The next step is move up over here, take the logarithm of both sides, ln both sides, ln 1.5, and then ln the right, so we have ln of 1.017875 to the 4t power. Okay? Why do we do that? Well, why we do that is because now, since it's a logarithm, I can bring this power out front here. So it'd be ln of 1.5 equals 4t ln of 1.017875. Now I'm in pretty good shape because what I can do now, notice here that t, well, that's 4 times t and then t time. These other things besides the t, they're just multiplied by t. So let's divide. I can divide them off both sides, and that'll get rid of them on the right side and leave me only t on the right side. So divide both sides by 4 ln 1.017875. Yeah, that'll cancel the 4's out, that'll cancel the logs out, and on the right side, I'll have t left. All right, now, the other thing is to figure out, well, what this number is. It's just a number. I can do the LNs on my calculator. Word of caution, though, when I have these two things in the denominator, be sure when you put those in your calculator, put parentheses around the whole denominator there. So I have ln 1.5, then divide that by parentheses for ln 1.017875. That gives me 5.72, and that's my time. Remember, in this formula here, the time is in years, so this is 5.72 years. And just a little other note, we were talking about quarters, so that's 5 years and 3/4 years, wasn't it? So 5 years and 3/4. All right, number 2. Number 2, we have Jill investing $2,000 in an account that earns 4.5% compounded continuously. How long will it take Jill's investment to double? Okay, well, first of all, formula-wise, look at the compounding. Here we're having compounding continuously. So referring back to our formulas, which of those two works here? Well, got the note there, compounding continuously. That's the one on the right. A equals P e to the RT. That's the formula of this one. A equals P e to the RT. All right. So we got 2,000. That's my P. E is the natural base, just base E. And then R, well, again, it's a decimal right there, but don't put 4.5 for R because, yeah, you still got to move it 2 places back, so that'll be 0.045 is R. T is what I'm trying to find. How long will it take? So that leaves us again with A. Well, we want our investment to double, so the future amount that we want would be double what we started with, the 2,000. So double 2,000, you got 4,000. So A here, yeah, A is 4,000. So this is what our formula is to work on number 2 here. All right, well, same basic steps to do this. First of all, I would get rid of the 2,000. Divide off the 2,000. Because that'll reduce that down right there. 4,000 divided by 2,000 is 2. So we have 2 on the left, and then the 2,000s cancel, so we have e to the 0.045t on the right. Okay, well, again, trying to solve for t, I need to get t out of the exponent. And so the way we do that is we need to do the ln of both sides. So I take, let's move up over here, take the ln of both sides, ln of 2, and then the ln of e to the 0.045t side. Okay? What that allows me to do is bring that power down. So I have ln of 2 equals 0.045t times the ln of e. Hey, but that's even much nicer than problem number 1, because what about the natural log of e? Yeah, the natural log of e, that reduces always, that's 1. So on the right side, I'll have ln of 2 equals, and then on the right side is just 0.045t. I don't have an ln left on the right side. Well, solving for t, so all I have to do, divide by 0.4045. So that'll cancel those out. So that'll give me my t. Take the ln of 2, divide that by 0.045, and I get 15.4 years. Okay? All right. Well, scrolling on down here, the worksheet, handout. Yeah, it turns out there are other applications that we can solve that have exponentials involved. One is the exponential growth or exponential decay models. And what I've done, I've written down here what the equations of such a things can look like. And so y equals y0 e to the kt, that's a good general model for exponential growth or exponential decay. Yeah, these, as it states there, these sometimes are used for population growth. Sometimes population growth, a lot of times population growth, I should say, is exponential in form. Also, radioactive substances, they decay exponentially. And so, yeah, we can use exponential functions to model those scenarios, and we'll look at both of those here. Now, first of all, notice the similarities between this and then the continuous compounding formula I'm referring to, a equals p e to the rt. Very similar. I'm just using y instead of a, y0 instead of p, e to the kt instead of e to the rt. So let's just note here what the things mean. So y, in the y equals y0 e to the kt model, the y would be the future amount, right? Just like the a is the future amount over there. So y is the future amount. Y0, the 0 just kind of means at time 0, it's y0 is the initial amount, like p is what you start with in that formula. Y0, that's the initial amount in this model. And then k, well, notice k is in the same place as r. Yeah, k is the rate of growth or rate of decay, depending upon what you got. And t, well, t is the time. And one note here, time could be in months, could be in years, could be in days, minutes. You just have to pay attention to your problem, what it tells you there. All right, now, another point to make on this model here. If k, it says, is a positive number, then the equation represents exponential growth. If k is negative, the equation represents decay. Why do you think that is? Well, if you recall, back when we were talking, starting to talk about graphs of exponential functions, if I had f of x equals a to the minus x, if my power, the x was in the power and it's an exponential, and the x was negative, you remember the graph looked something vaguely like this. And we pointed out that that's decreasing. It's a decreasing function. If f of x was equal to a to the x, just x, positive x, then our graph looked more like that. And so, yeah, that was an increasing graph going left to right. And so that explains why, yeah, if you've got, let's just say we've got y equals, let's say our initial amount was 100, e, and then I've got 0.02 t. Yeah, that is a positive power, if you will. So that's going to be increasing. Therefore, growth. A growth model. It's growing. Increasing from left to right. As time passes along, you're increasing. However, if y equals 100, e to the minus 0.3 t, yeah, that one's going to more closely look like the one here on the left, right? This decreasing model, because we've got a negative power up here, a negative in the exponent there. So that one's the decreasing variety, and so yeah, that is decaying instead of growing. So that's what we're saying. If the rate is positive, it's growth. If a is negative, it is decay. Okay? All right. Let's move on to number 3 then. Number 3, we're going to talk about town population of Smallville. It says Smallville is growing exponentially as given by, the population is by y equals 50 e to the 0.27 t, where t is the number of years after 2000. Okay? Question A, just so we got this. What is the initial population in the year 2000? Well, referring back to what we said about this model, this is the y equals y0 e to the kt. Where does the initial amount occur? Well, the initial amount is y0, which is the first, it's what is times the e, base e number. So yeah, this right here, that's our initial amount, 50. What is the growth rate? Well, the growth rate was, if we were referring back to this, was the k. So it's what's times the t in the power there. So in this case, I've got 0.27. That's our rate. Well, 0.27, usually we give rates in percentages. So 0.27, if I change that back to decimal, go the other way there. So it'd be 27%. That's our growth rate. So this town's growing pretty nicely. 27% growth rate. All right. All right, now, B, we ask this. In what year, according to this model, will the population reach 5,000? So we want our future amount to be 5,000, so that is the y value is 5,000. So I want to plug in 5,000 for y, and so that'll equal 50 e to the 0.27 t. All right? Well, does that look familiar? It looks a lot like one we've already done. How do we solve that? Well, ultimately we want to ln both sides, but before we do that, yeah, we got to get rid of the 50. So I'm going to divide both sides by 50. That'll get rid of the 50s on the right. 5,000 divided by 50, that's 100. 50s are gone, so I just have e to the 0.27t on the right. Now, take the ln of both sides. ln of 100, ln of e to the 0.27t. All right, so now that we're in a logarithm, the power, we can bring that down. So it'd be ln of 100 equals 0.27t times the ln of e. Hey, yeah, but the ln of e is 1. So this is just the ln of 100 equals 0.27t. So if I divide off the 0.27, that'll get me what t is. ln of 100 divide by 0.27. 17.06. Time in years. Now the question was, in what year will that? Well, that's close enough. I'll just say that's 17 years. So it's 17 years added to the 2000. So that'd be along about 2017, wouldn't it? All right. Okay. Number 4. For the substance plutonium-241, the amount after t years is given by the formula A equals A0 e to the minus 0.231 t. Note this is an exponential decay model, so we're decaying because why? Well, what's our rate? Here's our rate, and it's negative. Yeah, you've got a negative in that exponent, so that's decaying. So that is because the rate of growth is negative. So we've got a negative in that power. Okay. So a couple questions on this. If 600 grams of plutonium-241 is observed, find the amount left after 25 years. So we want to find the amount after 25 years. Now, we're starting with 600, so where would that go in our little formula? Well, that's the amount we start with, so that's A0. So 600 goes in for A0. So that'll be times e to the negative 0.231. And in this case, we've got 25 years, so t is 25. All right, how do we proceed here? Well, this is just meaning to evaluate. Just have to multiply that negative 0.231 times 25. It's be negative 5.775. And yeah, that then I do e, that's base e, so I just plug that into my calculator. E to the negative 5.775. Get what that is. It's about 0.0031. Then times that by 600. It's 1.8625. And notice this is an amount, and in this case we're talking grams, so that'd be 1.8625 grams. Okay? All right. B, here's what we want to know in B. Find the half-life of this substance. I'll give you the definition here. Definition of half-life is it's the amount of time it takes for half of the substance to decay. So a half-life is a time. I'm looking for a time here, t. See if we can figure this out. All right. So in my formula, since I did 600 in A, we'll just leave that in there. but I don't know my time now. And then the other thing is, I also know my future amount because I want the amount I start with to decay to half. So wouldn't that mean A would be 300? A would be 300. So this is my formula that I got. So solving that out, same old, divide through by the 600 to get rid of it on the right. So 300 divided by 600, well, that's 0.5 or a half, and that's going to equal negative 0.231t. Now what? I'll take the ln on both sides. ln of 0.5, ln of e to the negative 0.231t. The negative 0.231 comes out front. So I can do that in logarithms. ln of e, well, that's always a good one to have. That's 1, so I just have the ln of 0.5 equals negative 0.231t. Solve for t, all I have to do is divide by negative 0.231. And that'll give me my time. So ln of 0.5 divided by negative 0.231. 3.0, right at 3 years, 3.0006 years. Right? Okay. One more, and that is a logarithmic model. Turns out that an adult male elk, in a certain region anyway, has a relation. We can figure the relationship between the antler spread, x, and the shoulder height, h, by this formula. H equals 1/16 the log of x plus 40 minus 176. Okay? Those two are related that way. A wants us to find the shoulder height of an adult male elk that has an antler spread of 90 inches. Okay, so the first step here is just figure out where we would plug in the 90 inches. The 90 inches is the antler spread. What is represented by, what represents the antler spread in our formula? Well, the antler spread is x. So this is x. X is 90. I plug in x to be 90. So I have h equals, I don't know what h is, 1/16 log, I know x to be 90. So it'll be log of 90 plus 40, parentheses, and then minus 176. What do I do here to solve this one? Well, this is just evaluate. You know, you've got 1/16 times, we can simplify the parentheses, it'd be log of 130 minus 176. Yeah. Figure this one out. Just put that in our calculator. You know, this is the common log. Most calculators have that button on it, so I just put that in. Log of 130, 2.1139. Multiply it by 1/16, and then subtract 176. 69.2. And that's in inches. So the shoulder height is 69.2 inches. Okay? All right. Let's look at B. If the shoulder height of an adult male elk is 78 inches, approximate the antler spread. Well, in this case, I've got the shoulder height, and the shoulder height is represented by the h. So in this case, I've got h, so that's 78 over here on the left, and that equals 1/16 the log of x plus 40 minus 176. All right. What to do then next about that? Well, this one is a little more complicated, isn't it? Because, yeah, I'm going to have to solve a logarithm. I've got the x inside the logarithm, so I'm going to have to solve this logarithm equation. And so I know how to do that. What I need to do is, first of all, is to get the log all by itself. In other words, I need to get rid of the two other numbers, the 116 and the 176. Well, to get rid of the 176, I would add it. That would be my first step. Add 176 to both sides, and that gets me 78 plus 176, 254. 176's are gone, so it's just 1/16 the log of x plus 40. To get rid of the 116, well, that's 116 times the log, so to get rid of 116, I would divide by 116. So 254, divide that by 116. All right, now word of caution on that. I could round that off pretty well, but I wouldn't do it. You don't round off too much until you get to the end. This one, pretty long decimal. I would say at least 4 or 5 decimal places. 2.189655. That's 6 decimal places. And yeah, if you round off too much on these, it really skews your answer at the end. So yeah, just word of caution there. All right, so that would equal the 116 cancels x plus 40. All right, we said we know how to solve log equations. Once we get the log by itself, what do? We exponentiate both sides to the base of our logarithm. Well, there's no base showing here, but we know for log it's understood to be base 10. So I'm going to exponentiate both sides to base 10. 10 to the 2.189655 equals 10 to the log x plus 40. Why do I do that? Well, that's because the 10 and the log base 10 cancels out. So I have on the right side, I have x plus 40. Now 10 to the 2.189655, let's go ahead and see what that is. It's 154.76, let's say. Yeah, this is what I have then left. And so then all that remains then is to get x, so subtract the 40. Yeah, subtract 40, and that would mean 154 minus 40 is 114.76. That equals x, and x is in inches again, so it's 114.76 inches is my antler spread.